Hello. So we're going to start new information right now, and our final chapter is on line integrals and vector fields. And I got to be honest, there's a lot of applications of this chapter in other contexts. So if you go on to study physics or engineering or even more math, this is the chapter where things are going to pick up. Now, this is going to seem counterintuitive, but I'm only going to go so far in this chapter because I don't know what applications you're going to need. And since I don't understand some of those applications because I am not a physicist or an engineer, just know that this is one of those chapters where if you take an engineering or a physics course later on and you're like, wow, they said I should remember this from Calc 3, go find a Calc 3 textbook, open it up, and refresh. Okay. So before I just ramble on with nothing, let's talk about what a vector field is. Simply put, a vector field you've kind of already looked at when we did slope fields last year in BC. Now, vector fields are a little bit more complex than that, but you get the same idea. So I'm going to fold my computer here, pardon me, and try to kind of keep myself in the screen as best I can. Do. Let's see. Sorry, I know this is me learning how to use a good camera. So when we talk about these vector fields, really you want to think about slope fields. And down at the bottom of the page, you can see some 2D and 3D vector fields. Now, how were those drawn? They were drawn by basically taking a vector valued function. Again, I'm sorry for the moving camera there. You take a vector valued function here, but really it's a vector valued function where instead of it being in terms of t, all of the components are in terms of x and y. So I have some function h of xy and k of xy, and those functions create vectors. Okay, they create components of vectors, and then together they make vectors. If it's in 2D, you just have an m and an n. If it's in 3D, you have mn and p. Okay, that creates a vector field. The definition of a vector field is a function f that assigns a vector f of xy to each point in R. Okay, I still don't know what that means. Let's see what it looks like. So, if I were to look at A and it says match the following fields to their equation, and I have A, let's call this capital F right here. Off to the side, I'm going to pick a couple points. So, if I wanted f of 0, 0, I would put 0 in for x and 0 in for y. So if I put 0 in for y, I get 0 is the first component. And if I put 0 in for x, I get 0 for the second component, which means the vector at the origin is the 0 vector. So I shouldn't see any vector that comes out of the origin, and I really don't. So that wasn't really that helpful. Now let's pick another point. Let's pick f of pi 1. So if I put pi in for x and 1 in for y, when I put 1 in for y, I would get a 1 there. When I put pi in for x, I would get a 0 here. So at the point pi 1, I should see the vector 1, 0, which means at the point, let's say if this was 1, 2, 3, at the point pi 1, maybe that's, I don't know, here. Just pretend for a second. Okay, don't draw this. I'm just pretending. I should see the vector 1, 0, which means go horizontal, but don't go vertical. Well, that's definitely not in that field. I mean, even if I counted wrong, that doesn't look anything like something horizontal. Let's see what does. Ah, maybe this second one, because at the point 3, 1 ish, I see one of those horizontal vectors. Now, I am not going to do this forever ad nauseum and do tons of different points. So, what I'm going to look for is when is it pointing up, down, left, right. So, again, messing with the camera. So, what I'm going to realize here is whenever y is positive, my horizontal component is also going to be positive. In other words, whenever I'm above the x axis, I should have arrows that point to the right. Now, they might point right and a little bit up, but I know they at least point to the right. And then whenever y is negative, they should point to the left. So let's see, whenever I'm above the x axis, they should point to the right. Well, that definitely doesn't do it in the first one. Whenever I'm above the x axis, they should point to the right. Yep. Whenever I'm below the x axis, they should point to the left. Yep. So this second one is a good possibility. Whenever I'm above the x axis, do these point right? Yeah, pretty much. Whenever I'm below the x-axis, do they point to the left? No, not so much. So this is the one that has to be y comma sine x. Okay, let's move on to the second one. If I do the same kind of thing, now I start with negative y, which means whenever y is positive, we're going to point left, and whenever y is negative, we're going to point right. And if I look at the x, which is in kind of the y component, the vertical component, whenever x is positive, it's going to point up. And whenever x is negative, it's going to point down. So I need something in the first quadrant that points up and to the left. Well, of the remaining things, that has to be right here. Because in this quadrant, we are pointing up and to the left. Now, by process of elimination, C would be the last one, but let's figure out why. I have ln of 1 plus y squared. I have ln of 1 plus x squared, which means the least I could have is ln 1. And anytime either x or y or any number, honestly, ln of 1 plus something is always going to be positive, which means these two components are either 0 or positive, which means this vector field should always be pointing up and to the right, okay, except at the origin where it's not going to go anywhere. And that's exactly what this last thing shows. All of those arrows are going up and to the right to some degree. Now, if we come down here to a 3D vector field, in this 3D vector field, I have 4 options, 4 fields. Wow, look at that. You got to admit, that's pretty freaking cool. So there's a 3D vector field. What does this mean? Well, I don't know yet. If I look at 15 and 16, though, 15 is the vector field 1, 2, 3, and 16 is the vector field 1, 2, 1. Nope, 1, 2, z. Pardon me. Okay. 1, 2, 3 is a vector field that's always 1, 2, 3, which means no matter what point I'm at, I should see the exact same vector pointing in exactly the same direction. Okay, that looks pretty cool. So, exact same vector pointing in the exact same direction, huh? Well, which seems to do that? I'm pretty sure that's 4. Because if you look at 4, that seems to have the same arrow. All of those arrows are parallel. They point in exactly the same direction. That seems like it's pretty much it. Now, you might be saying, but Ms. Vibber, what about number 3? Aren't they going in the same direction? Not really. Some of these are going to the right and some of them are going to the left. So that's not going to work out so well. But in 4, they're all pointing in the same direction, okay, and have the same length. Now, 16 is 1, 2, z, which means it's always pointing in the positive x direction. It's always positive, pointing in the positive y direction. In this case, if you look at where x and y are, positive x direction would mean it should be always pointing this away. Positive y direction means it should always be pointing that away. Okay? So actually, the one I'm circling just to talk about it seems to be doing that. And z says when z is positive, these should be pointing up. And when z is negative, they should point down. And as a matter of fact, that seems to be exactly what this thing does. Whenever z is positive, it points up. Whenever z is negative, it points down. And it always seems to point toward these corners right here. So I'm pretty sure 16 is 1. All right, let's look at 17 and 18. So if we look at 17, it's x, y, 3. Since my z component is just a 3, it's always going to point up. And let's see, of my remaining ones, does anything always point up? Yes, it does. Right here in choice 3, those are always pointing up. The other ones are not. So 17, by process of elimination, is going to be 3. Okay. And then if we look at, last but not least, 18, I have x, y, z, which is going to kind of do its own thing. But when x, y, and z are positive, it should point at this corner. When y is negative and z is positive, it seems to point toward that corner. Yeah, x, y, z seems to look like number 2, which is kind of like, I don't know, if you wanted to think about it, what the Big Bang might look like. Okay, so it kind of looks like an explosion. Now, what's interesting to think about is could that be an explosion? I would argue technically no. So I'm going to go off on my own little path here for a second. If this were, say, the Big Bang, represented as a vector field, the arrows in the center toward where the source would be should be larger than the arrows on the edge because there's more velocity in the center than there is going to be on the outside. So if the larger arrows were in the middle and the smaller arrows were on the ends, then I would argue that that could be like a Big Bang kind of scenario. All right, we've looked at vector fields. I'm going to stop here and just keep making small videos to go along with this. I hope everybody's having a good day. I'm going to take a moment and stop this and start another one.